SwayamPrabha. Digital India. Educated India.
Good morning, gentlemen. We have been discussing the higher order elements. So in the previous class, we talked about how to develop the quadratic elements and cubic elements and so on for one-dimensional case. So now let's move on to the 2D case, which is of course the more important application. So let's look at this. Also follows the same thing as the 1D case where we use the Lagrangian polynomials. So here we use the Lagrangian polynomials in x and y directions or psi and eta directions. And then we take a product of all those things. Let's take this simple first degree element. So that's the linear polynomials. So what we took at that time is in the x direction, we took the two nodes and took two Lagrangian polynomials. So let's use the lambda 1, lambda 2. So we use the lambda 1 here for this one in the x direction or psi direction, and lambda 2 in this, the second one, 1 and 2 here. So this is linear, and then the same thing we do it for the y direction also. So they look like this. So this is lambda 1 in the eta direction, and this is lambda 2 in the eta direction. So this is linear and linear. We combine them and we call it as bilinear element, rectangular element. In the sense that we have taken the linear Lagrangian polynomials in x and y direction. So we take the product of this. So the various products is products of these of psi and eta. So we have 2 here, 2 there, and we get 4 products, and that's lambda 1 psi, lambda 1 eta, lambda 1 psi, lambda 2 eta, lambda 2 psi, and lambda 1. Okay, so these are in the basic directions, and then this combination of lambda 1 psi, lambda 1 eta is a product of this lambda 1 and lambda 1 here. So a product of these two obviously will have value of 1 here and goes to 0 here, goes to 0 here, goes to 0 here. So let's call this as node 1, and so this is node 1, and this becomes, so this you can see, so lambda 2 psi is 1 here, so that means it's 1 here, and lambda 1 eta, so that's 1 here, so that means that this is 2 and this is 3 and this is 4. So 3 is lambda 2 psi, lambda 2 eta, so that is here 1 and here 1, so that means that this is 3 and this is 4. So this is these are the properties of the shape functions where they will have value of unity at that nodal location and 0 at other nodes. So just like here for this lambda 1 eta, so it will assume a value of 1 here and 0 here, 0 here and 0 here, and so that's how it is. So if you look at maybe so 1, 2, 3, 4 here, and if you look at so at node 1 we have value of 1 here and 0 here, and everywhere else also is here. So I hope you got the picture. So this has value of 1 here, 1, and linearly goes to 0 on node 2, and so similarly here 4 as well as at node 3. So you can see that it varies linearly in the x and y directions, and if you take any other direction it may not vary linearly, in the sense that if you go along the diagonal here, so then it will have a quadratic variation. Okay, I hope you can get the picture, right? So that's why it's called bilinear. It is linear in x and y directions and maybe quadratic in other arbitrary directions. So this is how we develop a four node thing here. And then of course the xi and all that, they'll have the same thing. This is in terms of xi eta -1 to +1. You can also do it, for example, if you take x bar as x1 to x2 by 2 and h here x2 minus x1 by 2 and xi here x bar plus xi h. Okay, so this is the transformation between xi and x. A similar transformation you can also take it between y and eta. And of course you can take the derivatives in x, derivatives in xi, and accordingly you have to transform them. So let's take this is the bilinear element. So totally 4 nodes, you can see it. 2 on either side. Now let's take the next one. So quadratic on both sides. So it's called biquadratic. So 3 on so here 3 on x direction or y direction. So the 3 are, last time we have seen, in the case of linear element. So this is lambda 1, lambda 2 xi and lambda 3. So 3 in the x direction, right? And so similarly 3 in this is lambda 1 eta. So these are 3 in the y direction, and a product of all these things, product of all the possible thing here okay, product of all these things, for example, you can have lambda 1 xi, lambda 1 eta. So like this, so you will have 9 possible products, right? And so this is both being 1 is at this nodal location 1, right? Right, at this it becomes 1 and 0 here, 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 as well as here. So let us, so this is corresponds to N1 xi eta. This is node 1. So this is corresponds to this node. It has a lambda 1 is like this, node 1 here. And so similarly lambda 1, so it has a value of 1 here. So this is the location where it is, both are 1. And it becomes 0 here and 0 also here. And then let's put all these things 4, 5, 6, 7, 8, 9. So there are 9, for example, 9 also is there. So 9 like this. So if you want to make the shape function for xi eta, so then it should be a product of lambda 2 xi and lambda 2 eta, right? In fact, just to, for the sake of completeness, let me put it here, minus xi okay, so similarly here you can write for the 3 here. So like this, so we have xi eta and 3, 4 and so on. So like this, so you have 9 products and 9 nodes, and accordingly 9 shape functions, right? So this is how you can very easily develop even for the next case of bicubic. So this is 9 noded. So the next one will be a cubic, means 4 on each side, 4 into 4, 16. So okay. So let me just show it. So bicubic, which means that it is 16 node cubic element. So we will 4 on this side, 5, 6, 7, 8, 10, 11, 12. Okay, so this is a 16 node bicubic Lagrangian element. Okay, so like this, so you can develop it, and then the derivation of stiffness matrices is nothing but B transpose dB, where B is the relationship between strain and the nodal displacements. So that strain has the derivatives dou U by dou X, dou V by dou Y, and dou U by dou Y plus dou V by dou X. So you take the derivatives, and then take the derivatives, you have to get it in terms of X, so that means that you also have to transform. So that's number one. So there is one problem here. As you go for higher order elements, so there seems to be a lot of internal nodes that are coming here, which you cannot avoid, because if you take 3 on this side and 3 on this side, so you have to take all possible products. You cannot leave out any product just like that. For example, if you have a shape function here, so that will be 0 at these 4 points. So which means that you also need additional shape function corresponding to these nodes, right? So that's why you require nodes at these locations also. So if you look a little carefully, it's very important. So those nodes really do not contribute anything for inter-element compatibility, and so while assembly, so they will not be assembled of any nodes of the neighboring elements. So they just are only exclusively for this node. So if you can eliminate them, then it's at the element level itself, then it will be much better. They can be eliminated at the element level because they are not going to be associated with any other neighboring elements. So that's, of course, can be done, but it's a tedious procedure. Okay, there are matrix operations which can be done. You can eliminate them at the elemental stiffness matrix itself. So these 4 degrees of freedom can be eliminated. But if you look at that, another very important thing is that let's look at something known as Pascal's triangle. So this is a very useful concept in the mathematics, so where we talk about the terms that are available instead of xi eta, now here xi eta, right? So we use x and y. So this is 1 and the linear terms, and then and cubic terms. So like this you can write like this, you can keep writing. So the important thing here is that, so which are the terms that are present in the case of bilinear element and biquadratic and bicubic. If you see them, so then we can immediately see here that these are the linear is, as we say, they're the products of xi and e, Lagrangian polynomials in x and y directions. So what you can see if you go back here, so it is a product of linear terms in x and linear terms in y, by all possible products here. So that means that it consists of 1 x, y and xy. So that means that you have terms. This is for bilinear. So similarly for quadratic, biquadratic, you have terms 1x, the terms here are 1x square taken product with 1y square, right? And so you have the terms of 2x square here and y square here and product of this. Product of all these things, 1x square, 1y square. So this is for cubic. And so similarly, you also have other higher cubic will have this. One more term that need to be written here is the x cube, y cube coming from. Okay, so we can say this is bicubic and this is quadratic. And the innermost is, of course, bilinear. So the one important thing that we have to observe is that as you go more, then we have so many internal nodes which may have to be avoided or eliminated at the element level itself. That's number one. Number two is that if you look at the higher order elements, say for example cubic thing, so if you take this one bicubic, so you have all the terms x cube, x square, y square, y cube, and then you have higher terms x cube, y, x square, y square, x, y cube, and x cube, y square. So if you take this row, so you have three terms without completing x to the power of 4 and y to the power of 4. Okay? And so similarly, you still have higher order terms x cube, y square, y cube. So in this row of fifth degree polynomial. So the approximation here is not complete in the fourth degree polynomial or even fifth or even sixth. So these additional terms are there for the sake of constructing this element, but however it's not going to help the element, or it's not going to help to the point that it will not improve the convergency rate. Okay, so unless the row is complete, we cannot say that it's completely fourth degree terms are available. No, fourth degree terms are not available, fifth is not available, and sixth degree is also not available. So that way, so these higher order terms which are incomplete polynomial degree of that row will not help in the convergency rate. Like we said that h to the power of something, right? So here that is governed by the row which is complete. The convergency of the element is only governed by the row which is complete. So the higher order terms are there here for the sake of construction of this Lagrangian eliminate. So that's why is it possible to eliminate these things or anything higher order. Okay. So even this quadratic thing, even if you look at the quadratic thing, so look at this quadratic thing which is there. So look at the quadratic thing. So it has x square, xy, y square, but then there are three terms here, x cube, x square, y, xy square, x square, y square, which are there, but they are incomplete, right? So there are three terms which are incomplete polynomial degree of that row, and so they are not really helping us in constructing higher degree element. So for this, so we have another set of modified elements called serendipity elements. So if you want, we can write it here. So in this Lagrangian element, there are so many higher order terms which are incomplete. In that degree. In that degree, or to be more, row of terms. So as I said, unless that row is not complete, so it's not going to help in the higher convergency of the element. So for that we have serendipity element. So this starts coming from biquadratic. So this has only 8 nodes. Biquadratic Lagrangian has 9 nodes. So what we mean by this? So here so it has 8 nodes like this: 1, 2, 3, 4, 5, 6, 7, and 8. So this Lagrangian element has a node in the center also. So this has only 8 nodes, and so this is called the set of. Originally, this set of elements were discovered by chance, so that's why that term serendip is there. So here the shape functions, you cannot guess them as it is, but then now there are procedures to calculate or to construct these kind of elements. So N1 is like this. I'll write it for only for this one. So these 8 shape functions are like this. And 4 is 1 minus eta square. Oh, there's also a 7 here. Now there's also an N5 and 7. Yeah, so similarly N7 is 1 minus xi. I think these should be checked. They should be at N7. It should be. We should go to 0 here. -1, -1. I think it should be checked, please. These can be checked from any textbook. Okay, so those complete the shape functions, 8 shape functions. So people have arrived at by trial and error, and at that time they arrived at by just by chance. So that's why they call serendipity. So like this, so we have, I think we'll stop here for the moment and then we'll continue this discussion. There's a little bit more to discuss about these elements and then we'll continue it in our next class. Okay, for the moment, let's just take a pause. Bye then.